I'm gonna wait for about 1 minute. It looks like I have to admit all the students who are in the waiting room, which I didn't really intend to do so because it disrupt the lectures again and again. Somehow, so I'm gonna wait about like 1 more minute and then I will start. Okay, so let's start today. And I hope this issue will disappear, but what happens now is that whenever you entered this Zoom session, I have to admit you to this main session. So you're gonna be automatically be in the waiting room. And before the lecture, that's okay, but during the lecture, what happened is that while I'm talking, I will forget to look at this list of the people who are in the waiting room. So I hope to remove this problem, but just some safe bet for you, perhaps for 1 or 2 weeks, is to make sure you are on time. Otherwise, you might end up in the waiting room forever until the lecture is finished. I'll try for that not to happen, but I'm not sure I can guarantee you. Okay. Okay. So somehow. Okay, so what we're gonna cover today is a predicate logic. So, and then there are some reasons why we are studying the theories of programming languages from the predicate logic. And so let me start with the motivation. So this is more like a motivation for why we want to pay some attention to the studies of predicate logic, which is not a proper programming language, but studying about it will help gain some idea about what's gonna eventually happen. Sorry, I think I have to see the chat box as well as waiting room. Okay, so when we study each programming languages, there are 4 important concepts we're going to consider. The first concept that we will look at is something called syntax. Without talking about the syntax of a programming language, we can't really say anything, right? But as I said before, like on the first lecture, we don't really want to talk about the concrete syntax, the syntax as a string of symbols. We want to have some way to describe the syntax of a program in a bit more abstract way so that we can perform or carry out some systematic mathematical study about it. So so syntax is one important aspect of any programming languages we will consider. The second is semantics. Yeah, so syntax is more like it's a specification about what kind of things we can write and how we can represent those objects that we just wrote. And that doesn't mean that the program that we write denotes, say, computing factorials or something like this. On the other hand, the semantics provides the meanings to all of these objects that we write as a program. Then studying the semantics is what, I mean, it's a kind of basic tools that we will use to study the main features of our programming languages. So in particular, throughout the course, we're gonna look at two types of semantics. One is called operational semantics. And the other semantics that we'll look at is called denotational semantics. And when we study the predicate logic, I will give you some feeling about what denotational semantics is to look like. The third thing is something called inference rules. So inference rules appears in many different forms in the study of programming languages. And for instance, inference rules can be used to specify operational semantics, but inference rule can also be used to specify some reasoning principles about programming languages. Sometimes static analysis or automatic verification tools are specified in terms of inference rules. So this inference rule is another very important concept in programming study of the programming languages. We will look at a little bit about the inference rule when we study the predicate logic. So the last bit is a binding. So we'll study quite a lot about substitutions and various properties of our programs with respect to the available, program variables. And in particular, we're gonna look at when some programming construct introduce a bound variable into the program. And there are a little bit of the issues that we will have to consider. So some study about the binding is another important aspect of the programming languages. So what we'll do is we will study all these concepts in the context of much simpler language called in predicate logic. But I'm gonna present the study about these concepts, actually not the third one, but third and fourth one. But I will present a study about them in a bit kind of sub-language of the predicate logic, which is called integer expression first. So what we were going to cover today is language for integer expressions. And maybe on the next week, we will extend what we learned today to the predicate logic that will give you an idea about what these four important components in the study of programming languages look like. Okay, so let's start with some kind of introduction to the integer expression. So integer, you already experience integer expressions a lot when you write standard programming languages. So if, for instance, some of the typical integer expressions are like variable x plus and 3 times variable y, or sometimes you may write variable z divided by number 4 and plus 7. So this is integer division. And these type of integer expressions appear, in nearly almost all the programming languages that you played with before. And so we're gonna carry out the formal study about these integer expressions. So, and then in particular, we will look at we'll specify the syntax of such an integer expressions, as well as its semantics, and we will also study some about properties of the semantics of such integer expressions. So to start with something first. First thing is a syntax. The syntax of these integer expressions, we want to specify the syntax in a way that the syntax is more suitable for study on programming languages. Maybe not suitable for parsing, which is converting each string into some syntax trees which can be manipulated by the compiler. That's not what we care about. But the kind of syntax we want to specify is some syntax which describe these integer expressions in a more abstract way. So there are specific terminology that's used to describe such a syntax. So this syntax is called abstract syntax. And then this abstract syntax, the elements of the abstract syntax is called abstract phrase. And usually the abstract syntax is specified by abstract phrase is specified by something called abstract grammar. So, and intuitively, what these things tell us is that these are the syntax, phrase, and grammar which don't care much about parsing. It's all about representing programs in a parsing independent way. Okay, so in an abstract way, but it captures the existing while capturing the structure of the program. And so the abstract so for the abstract grammar for the integer expressions, it looks like this. Int expressions. So integer expressions have a multiple case. The first case is a constant, like number 1, 2, and so on. So there are constant integer expressions. And then another integer expression is variables. The third is negative symbols, the negation, not negation, but single minus sign. And then also we have binary operations. Integer expression. So we can add two integer expressions. Also, we can subtract, multiply, and divide. And in the textbook, we also use, John considers this remainder, which is the modular operations between two integer expressions. Okay, so this is something called abstract syntax. This is pretty similar to the context-free grammar that you perhaps encountered in either discrete mathematics, discrete math course, or in the compiler course. But there is a main difference between the specific context-free grammar that we use and in the specification of a programming language for parsing and this abstract grammar. For this grammar, if you view this as a context-free grammar, this is something called ambiguous because it doesn't really tell us. So if we have an expression like x plus y times z, okay, this grammar tells us whether this will convert it to, if you convert it to an instance of this grammar, it should denote something like this, or it should denote so this grammar itself is ambiguous about whether the string that you see, x plus y times z, should be converted to the tree that's written on the left-hand side or the tree that's written on the on the right-hand side. What does this mean is this grammar doesn't tell us whether we should first add them and then multiply, or we should first multiply and then add later. So the grammar doesn't really say this. So this is something called ambiguous grammar, and it's not very suitable for when we want to describe a parser for the programming languages. But that's not what we're gonna do. So we will use this abstract grammar. So in some sense, we are saying we are not very much interested in this process of converting string to so-called parse tree, which is an instance of the grammar. Instead, we are only focused on these trees that we are directly work on these trees. So our starting point is not a string, but these trees. So that's why this is called abstract grammar. This is a grammar which doesn't really care much about how to convert strings into trees. So it's mostly can view this as a specification of finite trees. And the element, so this is an abstract grammar for integer expression. An abstract phrase of this integer expression is a finite derivation trees according to this grammar. So one example is we can have a tree which have only one node, that's and associated value is equal to 1. That correspond to this the first production, which say number 1. Another is another single tree which have only one node, like 2. And then we may have something more sophisticated like the trees that we talk about here. So this tree is obtained by first using the production rule for multiplying two integer expressions here. And then we, on the left-hand side of the integer expression, is going to be the variable z, so that corresponds to this case. And then the right-hand side is variable z, left-hand side is the plus sign, which corresponds to here, and so on. So this tree is an instance of this abstract grammar. So abstract phrase means these type of trees. So this is another example of abstract tree. Abstract phrase, this is another example of abstract phrase. And abstract syntax is a collection of all these abstract phrases. Okay. If you collect all these abstract phrases, this is called abstract syntax. So one way to think about this abstract syntax, abstract phrase, and abstract grammar is that abstract grammar is a grammar or ambiguous context-free grammar whose main purpose is to specify collection of finite trees. And specified finite derivation trees, they are going to be an abstract phrase, and collection of all those finite derivation trees form an abstract syntax. Okay, so that's one way to understand this abstract syntax, phrase, and grammar. Okay, and another way to understand, mathematically understand this, is in terms of initial algebra. And this more abstract view, I mean, if you are more inclined for mathematics, and this more abstract view will provide you a very generic definition, and it will also help you to analyze, see why certain principles are okay. So in particular, I'm gonna talk about something called the syntax directed definition and also structural induction. And justifications of them can come from this is a more concrete view that I describe in item 3, but it also can come from more abstract view that I'm describing in number 4. And actually this number 4 is more fundamental reasons why this type of principles that are valid in this case. But anyhow, so this initial algebra is a way to, I mean, it's coming from so-called universal algebra, and it's defined like this. So we first have to say what algebra means. Algebra means nothing but sets with operations. So one example of algebra is a group. So it's a group of integers. So it has an underlying set, which is a set of all the integers. And then it has an operations, operations and constants. So it has a constant like number 0, and it has an operation like a binary operation called plus, and the unary operations minus sign. So I write it like this. As a unary minus sign. So this is a unary minus operation. Okay. So this is a one example of algebra, some set together with constant and operations. And another example is we can think about some real numbers which are greater than 0. And then constant may be equal to 1. The one constant is number 1. Operation is a multiplications. And then maybe it doesn't have to, we can end at this point, but we may also have some unary operation, which is inverse. Okay. And so now for each algebra, we also talk about something called the signature. Intuitively, signature can be understood as a type of an algebra. So what does it say? It specifies how many sets we are talking about. So most general case, it talk about we have two underlying set. That's going to be UNT. So it's an unknown types UNT, which denotes two underlying set. And it say we have three constant C1. The first is an underlying set U, C2, which is an underlying set T, and C3, which is an underlying set U. And then it specifies an operation, say there's an operation 1 that take 2 U's and return U, operation 2 that takes 2 T's and return T. Okay. And you can view this. This is pretty similar if you are familiar with Java. And this is the intuition is quite similar to Java interface. Okay. So this signature specifies a type of an algebra. So signature, we're gonna write it as an S. Algebra as an A. And we will write, say, algebra A has a signature S. If A has the type of A is actually S, which means if our signature looks like this, then algebra A should provide a set, for U, also another set for T, and some constant C1, put an underbar to mean a constant value which belong to set U, because our types say the constant C1 should belong to U. So that's why we have here constant C2, which belong to set T, and so on. And then some operations of 1. In this case, is going to be a mapping that takes 2 arguments of type U and return U. So it's a mapping that takes 2 elements of type U, of set U, and then returns another set U, element in set U, and so on. So that's algebra, and that algebra will have this signature S. So by using the same analogy to Java, this algebra can be understood as an implementation of Java interface. Okay. So typically when you implement the Java interface, we implement it by class. So this A can be understood as an implementation of a class which have the right type which is this specified by this signature S. And this type of, this kind of signature and, these signatures and algebras appears in can be used to formalize many things in mathematics. So very popular signature is a signature coming from group. Okay, for now, okay, so for today, I'm only going to consider the signature which have, maybe just highlight, which have only one type U, okay? So I'm not going to consider the signature which have two types like U and T. I'm only going to consider signature which has only one type U, because that will simplify many things today. Okay, so let's coming back to this signature for the group. Signature for the groups. Sorry. Right. Signature for the groups will look like this. It will have some set U, and then should have a constant unit, which is an element of U, and then we should have an binary operation. They take two arguments and return U, and we should have an inverse operation, which takes U and return the U. So that's a signature of the group. So it doesn't tell us what U is. It just says there is some type, which U, and there is an element in the type called E, and there is a binary operations and a unary operation. And then implementation was algebra, which have this group signature, is these two algebra that we see on the top. These are the algebras of the signature S group. Okay, why is that? If you look at this, the signature set, we should have a single set, and in both cases, we have a set Z and R, the positive real numbers. The signature set, there should exist some elements E in the algebra. Then we have an element 0 in the first case, 1 in the second case, and so on. So for binary operation, it exists in both cases. Unary operation also exists in both algebras. So this is a signature for the group. Okay. So now, this is a, okay. So let's use this algebra formalism to talk about the signature of the integer expressions. Okay. So I said more mathematically, the syntax of this integer language is an initial algebra. So I'm going to explain what initial means, but it is an algebra. Okay, so which means that we have to talk about the signature and also the algebra for the signature. So the second example is for integer expressions. For integer expressions, the signature looks like this. Signature have one underlying type. It doesn't say what it is, but there's one underlying type. But there are infinitely many constants and finitely many operations. So what are the infinitely many constants? It is a constant like all these constant numbers are going to be an element of the signature. So it doesn't say number 0, what we are thinking about. It just says there's a symbol 0, whose type is U, symbol 1, whose type is U, and so on. And then also it said for each variable that we can think about, it also said this variable is also, it has a constant that corresponding to the variable. So we have a constant named X, whose type of type U, another constant Y, which has a type U, and so on. So these are coming from variables, and these are coming from constants, constant integers. But as I said, this 0, 1 doesn't mean anything. Okay, it's just some symbol. So it's, you can think of it as just yeah. So 0, 1 are just on some symbols whose meaning we don't really know. It's a bit like in Java interface. If you declare some method and write down its type, I mean, you are not really providing what it means. You are just introducing some symbols for it. So we have symbols like this, and then we also have some operations plus, unary operation minus, which take u and returns u. And so, but again, this is not, we don't really, when you write signature, we don't really say this is a minus operations. We are just saying there is some operation which take u and return u. And there are multiple binary operations, division and remainder, which take two elements of type u and returns type u. So that's the signature for integer expression. And what is an algebra? And this algebra that I described to you, the abstract phrases that I described to you form an algebra. This is called, I think what I wrote, finite trees. So this is an algebra of finite trees. So we first have to specify this u, which is what u type u means, which means that we have to write down the set, and that set is all the finite derivation tree according to the grammar. So there are, in this case, countably many of them, but this set isn't infinite. And for number 0, we have a singleton tree, the tree with only one node, which is tagged with 0. So that is our interpretations of, what this algebra says, this interpretation of this symbol 0 in this algebra. And we also have a finite, this singleton tree, which is labeled with 1, and so on. So these provide correspond the elements for this symbol 0, 1, and so on. Variable x the same, the singleton tree, and y is a singleton tree, and so on. Now for unary operation, we have to define an operation that takes finite tree and then returns finite trees. How you do it? So that this minus takes some tree. So I will write tree as this triangle. And then what it returns is that it just puts minus sign on top of this tree. And so, and then I think you can kind of understand what this plus minus should be. In the case of a plus, it's binary operations. You take 2 finite trees and return finite trees. But what it does is that it takes 2 trees, and then what it puts plus sign on the top and construct a new tree. And other binary operations are defined in a similar way. Okay? So this is the algebra. What abstract syntax, what abstract syntax means is mathematically it denotes this algebra, okay, with respect to the signature. So abstract grammar, we can view this as a specification of this signature. In a more familiar, slightly less mathematical terms, and abstract syntax is really about, it is describing this algebra, and then elements of this underlying set of this abstract, this algebra is going to be abstract phrase. So then you might ask, okay, what is so special about this particular algebra, right? So that's a finite tree. Okay? So that's some natural question you can ask. The reason we are asking it is because we can actually have another algebra, which is write it as an A prime. It can be defined like this. And in this algebra, underlying set is, it consists of subsets of variables. So I'll write it like a 2 to the bar. This means it's a collect. This is a consists of all these, all the subsets of bars. Okay. So this is a set whose element is a subset of variables. And we can define like this. Then we say number 0 corresponds to the empty set. So 0 corresponds to this. And then 1 corresponds to the empty set. So on. And then variable x corresponds to the singleton set x. Variable y corresponds to singleton set y, and so on. And then for minus, we can say minus if it provides a set v0, it just return v0. And for plus, say if we provide two set v0 and v1, sorry. So v0 and v1, it returns their union. Okay, so then multiplications and division and so on, they all behave the same way. Okay, so this is another algebra for the signature as integer expression. Okay. And so this question that I raised here is why we pick the algebra on the top when we specify the abstract syntax instead of the algebra below. Okay, what is, is there anything special about this particular algebra that we define on the top? And that brings us to the next part, which is the initial algebra. But the special thing about this, the answer here is that it's an initial algebra. And in fact, we can actually change this on to D, which means in some sense, there is only one initial algebra that's defined by this signature. So that's the answer that I'm gonna tell you. Okay, but to talk about initial algebra, we have to learn a little bit more about this universal algebra. So we learn about this algebra and then the signature. So next thing we have to look at is algebra homomorphism. So homomorphisms is intuitively is a map between two algebras of the same signature. Such that the map preserves the constants and operations. So if you maybe took a course on group theory, you heard about homomorphism quite a bit, and it's essentially the same thing. It just preserves all the things that we have operations. Yeah, all the things that we have in the algebra. So here are the more formal definitions. Assuming the signature has only one type. So we have a signature S. Let's write it like this. Have a type U, constant C1. Okay. C1 of type U, set of type U, so on. And then we also have an operations which take some multiple elements of U and returns U. And operation 2, another multiple elements of U and return U. So in this case, and suppose that we have two algebra, A1 and A2, that have a signature S, which means that A1 has an underlying set. I will just write using capital U. So this is a set from the A1. And we have an operation. So I will write this superscript 1 to means that this is a constant that belong to set U1. Constants that belong to set U2, and U1, and so on. And we have an operation in this case, which is a function that take multiple arguments of U1 and return an element of U1. And then similarly, we have, so that's an algebra for the signature S. A2 is also an algebra for the same signature, but in this case, the underlying set may be different. And all these constants, I mean, of course, they are going to be, they may be different from the constants from A1, C2, 2, C1. And then operation, keep making mistake. Two. This. Then now, what do you mean by homomorphism? It's a function f that goes from U1 to U2. So maybe just write in these notations that goes from U1 to U2. So U1, I'm going to denote U1 as a bar A1 to mean the underlying set of this algebra A1. U2 is a bar A2 to mean the underlying set of algebra. So function is a homomorphism. If for constant, it preserves constant and the operations, which means that for all constants, Cj, what we have is that if we interpret Cj, well, we find its the meaning of Cj in the first algebra, and then map it to F, that will be the same as its meaning in the second algebra. So it really means preserve the constant. And then the second condition is for operations. For operations like of one of I. So we said if we evaluate these operations, ith operation in one with parameters, let's call it x1 up to xn. So we take x1 up to xn, they all lives in U1. And then apply this operation I according to the first algebra and apply the map F. That will give the same result as applying this operation in the second algebra after mapping all of its arguments using F. So U2 and so this is the definition of homomorphism, but intuition is it means the first condition means preserve constants. And then second condition really say preserve operations. Okay, so now so we can now define the notion of initial algebra. And we say that on algebra, A of a signature is called initial. If for any algebra of the same signature, of the same signature S, there exists a unique homomorphism F from I'll write it like this: unique homomorphism that goes for F from A to B. Okay. And it's really important that we talk about this. We talk about both existence, which means there is a homomorphism F that goes from A to B, but also talk about uniqueness. So there is no ambiguity about this. And both of this existence of a uniqueness, I'm going to tell you later, they are all related to the structural induction principle. And then something called syntax directive definition. For integer expression. So most programming languages, we almost always use induction, and also we almost always use so-called syntax directive definitions. That is because, from more abstract sense, that is because we are really defining the syntax of a programming language as abstract syntax of programming language as an initial algebra. Okay. So now here's some exercise I want you to do. Okay. I'm claiming in algebra A of finite trees, for which have a signature for the integer expression, is initial. So, and then actually in my notes, I ask you to prove this, but I don't expect you to prove this. But there is another things that I gave you as an example. I'm gonna soon go back to the part so that you can understand this. But here's an exercise. So this is actually an initial algebra. And we thought about another algebra called based on the, what did I write? Yeah, just I prime, where the underlying set was the collection of subsets of variables to the bar, and so on. So this is one thing that we seen, that this was also on another algebra for EXP. And because it's an initial, there has to exist a unique homomorphism from this algebra of finite trees, which is really the abstract syntax, to this A prime. Okay, so construct, because it's a unique, we can say the unique homomorphism from A finite trees to A prime. Okay, so this is an exercise number 1. So I'm gonna give you another exercise. Another exercise is that if A and B are both initial algebras, of the same signature S. So if that's the case, then there exists homomorphism F that goes from A to B. 예, 감사합니다. And G which goes from B to A, such that they are inverses. So F G followed by F is an identity on A, and F followed by G is an identity on B. What does this mean? This means that if we have a structure, the map that preserve all the operations and all the constants, the Fm preserve everything, G preserve everything, and then they are mutually inverses, which means essentially A and B are the same. So in this case, we are saying A and B are isomorphic. So in this sense, I mean, what this really tells us, there is only one initial algebra. So if we define the abstract syntax as an initial algebra of abstract grammar, so abstract grammar, I said, correspond to signature, abstract syntax correspond to an initial algebra. So if you define abstract syntax as an initial algebra of abstract grammar, there are no ambiguity because all the initial algebras are going to be isomorphic. So these are the two exercises I want you to do. I will give you maybe 5 minutes to think about this. So maybe I will, yeah, I mean, it's a bit difficult to show everything, but here's the problem. I hope you remember the problem. And then, so the definition of I mean, these two algebras that I talk about are given here. So the one algebra is here, and the other algebra is this guy. Okay, so these are the two algebras, and the first exercise is ask you to show construct unique homomorphism that goes from A finite, this algebra, A finite trees to A prime. So that's the first exercise. Second exercise is that ask you to prove if we have two initial algebras of the same signature, they are isomorphic. So I will wait about 5 minutes, and then I will give an answer and then move on. So by the way, if you have any questions, just like Gabrielle, you can ask questions in the chat box. Also, if you prefer, you can ask questions in Korean. That's also no problem. So Songmin asked the difference between the A prime constant do not have to be different. Okay, the constant the same can be mapped to the same constant. That's also fine. So in A prime, as you pointed out, the 0 is an empty set, 1 is an empty set, so they are the same thing. So it's a bit like in Java, you have a two method of the same signature in Java interface. You can implement them exactly the same code, but that's not a problem at all. So that's the same situation, analogous situation to what's happening in A prime. Okay, so let me show you typically in offline, I go around and see how you're working on the exercises, but online, I think it's impossible. So I will just give you an answer here. So for the first question, which is ask you to construct a mapping from finite trees to this set of between two algebras, we have to build a map. So for exercise 1, so we have to build a map F that goes from finite trees. Yeah, there's always an initial algebra. So there are some restrictions on signature, which I didn't really explain to you everything, but every signature have an initial algebra. So finite trees to, this looks weird. So finite trees to the set of variables. So I will define it more formally later, but really what it does is that it takes finite tree and it returns all the variables all variables appearing in trees. So it's not like a full mathematical definition. We will look at the mathematical definition here, but what it does is that it takes tree, and some node of the tree will be labeled with variables, and we just collect all those variables and return it. Okay, so that's what this operation is doing. And in fact, this operation we're gonna study more formally soon. It's the very well-known operation, which is sometimes FV. It's an operation that computes the free variables that appearing in an integer expression. So that's a solution for the first exercise. And you can actually show that's the unique homomorphism that goes from this between these two algebras. For exercise 2, I ask you to show if I have two algebra A and B, and of the same signature, both initial, and they are isomorphic. Okay, how to do this? And showing this is also not very difficult. So because A is an initial algebra, there is a homomorphism F that goes from A to B. It's a unique homomorphism that goes from A to B. And because B is an initial algebra, there is also a unique homomorphism that goes from B to A. It's called G. Now it turns out if you have a two homomorphism, if you compose them, that becomes also a homomorphism, because conditions of the homomorphism is about preserving constants and operations. And then composition works really well with respect to this preservation requirement. So if these two things are homomorphisms, so therefore what we can conclude is if you compose F and G, which is a mapping from B to B, this is a homomorphism. And then G and F, that goes from A to A, that is also a homomorphism. But there is actually a very simple homomorphism that goes from A to A. But identity function, which doesn't do anything, map elements to itself, B to B, is a homomorphism. Because it doesn't do anything, it preserves constant and preserves operation. Also, identity function on A that maps A to A is also a homomorphism. Okay. Now, if you take a step back and think about the situations, we have an initial algebra A. Initial algebra is also an algebra. So from algebra A to homomorphism, algebra A to itself, there is only one homomorphism. Okay, that's the requirement of the initial algebra. If between initial algebra to some algebra, in this case, it happens that they are the same. But because of the initiality, there is only one homomorphism, which means that this guy and this guy, they have to be the same. Okay. And by the same arguments, similar arguments, we can show that, this F composed with G and identity on B, there has to be the same by the initiality of this and this of P. Okay. So we just show that, this is exactly what we are supposed to show. F composed with G is an identity, G composed F is an identity, and that's what we showed here. So the proof is really simple, but this proof shows that given a fixed signature, there is only one initial algebra. Okay. Now let's go back to our. And the important bit is that for any signature, initial algebra exists, and then the abstract syntax is really an initial algebra. And this finite tree construction is a way to construct initial algebra. Okay. So this is the important bit. So just to come back, well, all these theoretical development, what it really tells us is that more mathematically, abstract grammar is a specification of signature, and abstract syntax is really an initial algebra of that signature. So, the system said my internet connection is unstable. So if you have any issues, please say something in the chat box. Okay, so, it's nice that the syntax looks like it's nothing that we can think about, have some nice mathematical structure, but okay, but then there is some more things. It's not just about some nice mathematical, the paraphrasing of the syntax. There is actually something that we can get out of it, and they are so-called syntax directive definitions and the induction principle, the structural induction principle. So I think the item is maybe now we have 4, 5. Okay. So now what we have, this is so-called syntax directive definition. So suppose, these are, so when we study the programming language, we often have to define a function f that takes that takes abstract phrase and returns something. And return something here. And one example is what I just told you before, which is the free variable operation, which take an abstract phrase, which is, you can view this as a tree representing a program. And then it returned the set of free variables in this. And these are the kind of things that we want to define. Of course, you can define it in a more kind of not very formal way, like the one that I just did here, but there is some formal way to do so. And that tells us, what it tells us is that we can define such a function inductively. So syntax directive definition is a mapping. Is a map over abstract phrases. So now is it okay? I think because it may be because of some internet connection. Okay, so I will say a few more words, and then let's see whether this the notes can. There's still a delay. So syntax directed definition is a map of abstract phrases defined inductively. Okay, so when we do the syntax directed definition, here's a very standard recipe. So you can think of this as a definition of recursive functions on abstract phrases or finite trees from the abstract grammar. And what we do is that we look at all the cases of the abstract grammar or the production rules of the abstract grammar. So in the production rules, we have constant case, and C. It's a constant number case, like a number 0, 1, and so on. And also we have a variable case, and we have a unary operation case. So I'm going to write it like this. This means unary operations, and with the expression E prime. So we have, if we have an integer expression, first case is a number, second case is a variable, third case is the unary operation. The fourth case is a binary operation, E prime plus E double prime, and binary operation can be, let's only think about plus and multiplication. Okay, we have two binary operation like this. Okay. So we have these cases. That's coming from the production rules of, they are coming from production rules for integer expressions. Are you okay now? Is it still, there is a lag? Okay, I take silence as something, everything is okay. So I think what I will do is I'm recording this lecture. So the recorded lecture will be uploaded to the KLMS. So sorry about this, but if you can, if everything is, if it doesn't work, then I will, you can have a look at it in the recorded lecture. Anyhow, I think we have about 5 minutes. So what's going to happen is that I will explain this today, and then maybe I'll go over it again on next Monday. So if you don't understand what's really going on, that's okay, because I'm going to do the review about what's happening, this material here again. Okay, so the idea of syntax directed definition is to define something inductively. So this is the important bit. And And then there is actually another important bit that we have to do. We have to, respect. When you do the inductive definitions, inductive call or recursive call should be only about immediate subphrases. Okay, so this immediate is important. So let me tell you what I mean by giving an example. So in the syntax-directed definition, we define some functions that takes expression and then return something. But in the body of the function, we do case analysis. So we said expression E is an integer constant, we do something, variable, we do something, and so on. Now, but when we define this, the case for the plus and like multiplications, so we're gonna say, in this case, we return this function something, but what returns is maybe involved, when we return something, we may do the recursive call, but recursive call should be only about immediate phrases like E prime and E double prime. So we are not going to look deep inside E prime and do further case analysis. We just do, in a sense, level 1 case analysis here. So here's an example of this syntax-directed definition. The connection is okay now, or it's still unstable? Nobody is following me, or okay. So then, just like I said, I'm gonna tell you a little bit, and then I will go through this again. So for the example, maybe I hope you can still see the screen. Example is a free variable for expression E. So it's defined like this. It's defined by the case analysis. The first case, given expression is an integer. So then we just return, maybe write it as a more mathematical form. We write it like this. If E is an integer, then we return empty set, because it doesn't have any free variable. If E is a variable, we return a singleton set X. And if E is a minus sign, then what we do is that we make a recursive call, and then we just propagate forward the outcome of the recursive call directly. And if E is a plus sign, so then we make a recursive call for the first, and then we make a recursive call for the second, and then we take their union. Okay, the multiplication is the same. We make a recursive call for the first and second, take their union. So this is the inductive definition, and what all these machineries of initial algebra and the finite tree and so on, what they guarantee is that this always is well defined. Because our syntax or abstract syntax is initial. So this is an abstract region, but more concrete region is the syntax consists of finite trees. because it's a finite tree, all these recursive code will hit the base case eventually. Okay, so sorry about the bad internet connection, but I'm gonna upload this recording to the course webpage, and then we will go through, start from number 5 in the next week. Okay, thank you all for attending this lecture, and I'll be here for about 5 more minutes, and yeah, so that's it for today.